Okay, so last time we finished up talking about how when electricity is sent over a distance, it's sent at a very high voltage. And I explained in words that the reason that that is to minimize the current because a large current is a lot of heat and that would be a lot of power loss. Um, and we don't want that. We want all of as much of the energy that we have made at our power plant as possible to make it to our homes. So let's do a numerical example with that. So practical power transmission. So we want to provide power to a small city, and the power plant generates 40 megawatts of electricity. It's AC. The only reason that we're saying that it's AC here is because we want to make sure that we are making a point to say that this is something that's going to work with the transformer. So induction only works with AC electricity, but we don't need to worry about any special formulas with that. The power plant is 50 kilometers away from the city. That's about 30 miles, so that's a pretty typical distance. And of course, we need now 100 kilometers of wire because, as we know, current needs a loop to travel. So it can't just travel there; it has to travel there and back. And this long 100-kilometer wire has a resistance of 7 ohms. All right, so let's step through this. So I'm going to just put up the PowerPoint on this so that I can show you some worked answers on our piece of paper here. All right, so let's write down what we know. We know that the power is 40 megawatts. Mega is a prefix for 10 to the 6, so I'm going to go ahead and convert everything into regular old units so that I know that I don't have to worry about any unit conversions. So power is 40 megawatts, and the length of wire is 100 kilometers, so I'll write that as 100 times 10 to the third, because kilo is 10 to the third meters. And the resistance of the wire is 7 ohms. And so the first question asks us for current. So for part A, we have want I. Okay, so we have P and R, and we want I. We are also told voltage. So we also know that the voltage is 25,000 volts. So we have power, R, V, and we want I. So there's 3 formulas for power. So the first one is power is current times voltage. The second one is power is I squared times R. And the third one is voltage squared over R. So those are our 3 formulas. And these formulas, when we use these formulas, as always, we are looking for a formula where we know 2 of the 3 things in the formula, and we're looking for the third one. Okay, so we want I, so we're immediately going to these 2 right here. And we're told about this voltage, so I'm going to go ahead and plug in this one. So we'll say that I is P over V, so that's 40 times 10 to the 6 watts divided by 25,000 volts. And 40, and that is 1,600. Before we put a box around it, we always think about sig figs. So if you come back to the problem, you'll see that I didn't realize I had cut off so much of that. So if you come back to the problem, you'll see that there's 3 sig figs or 2 sig figs for all of these numbers. So we want this to be 2 sig figs, and it is how it is right now. So that would be, that's 2 sig figs right there as we wrote it. So for part B, what's the power dissipated in the resistance of the transmission line of this current? So we want P, and we I think we can probably use any of these formulas to solve this problem. So let me see if I can find a better way here to see all of this so that I'm not cutting off my formulas. Okay, so we want P, and we know I. So we want to make sure, probably, this one would probably work, but let's stick with one that uses this current that we just solved for. And so really, let's use one of these. So this one looks easier to me because there's fewer buttons for me to push on my calculator. So I'll say that P is I times V, which is 1,600 times 25,000. And that is 40, 1, 2, 3, 4, 5 times 10 to the 6th watts. And I've specifically written it this way because, oh, something is not right. This is the power coming from here, and this is all of it. So why was that the wrong equation to look at? So the reason why this was a bad equation to use is, of course, I just got that all of the power is dissipated in here. So what I have actually solved for is not the power dissipated on the line, but the power supplied by the power plant. And while that is nice, it's not the answer that we were looking for. So a little assessment check tells me that this is probably not the right equation to use. So we'll cross that one off and go from there. And that's a great example of what you do when you get nonsensical answers. So always think about your answers. Okay, so that one didn't work. Let's try the next one. P is I squared times R. So I have 1,600 amps times R, which was 7. That makes me feel better because this question specifically asks about the power dissipated by the resistance of the transmission line. So I like that I'm getting an R there. So times 7 ohms. And that is 1792 with 4 zeros. And that feels a little bit better. So again, if I move this, let's go ahead and write it in mega so that we can compare these two numbers. So if I move it 1, 2, 3, 4, 5, 6 decimal places, that's 17.92 megawatts. I'll round that to 2 sig figs. So I'm going to go ahead and write that as 18 megawatts. So running it at this still pretty high, but not high enough voltage, we have lost, we started at 40 and now we're down to 18. We've lost almost half of the power that was generated by that power plant, just getting it to your house. So we don't do that. Instead, we do what C says. Let's, instead of 25,000 volts, do this at 50,000 volts. So let's redo what we did here, okay? So we did I is P over V before, but now instead of 25,000 volts, we're going to plug in 500,000 volts. So I is 40 times 10 to the 6th divided by 500,000 volts. And I have 80 amps. So quite a bit less. If I want to write this as 2 sig figs, I'll put a little decimal here before I put a dot on around it. Another way I could write this as 2 sig figs would be 8.0 times 10 squared amps, and that would be just fine too. And for part D, which I have cut off, well, I guess we're not going to see part D. I'll put it up here. What's the power dissipated in the resistance of the transition line for this higher voltage? So let's redo what we did in part B. So we'll do I squared times R. And now we use our 80 amps times 7. 80 squared times 7 gives me 44,800 amps. Before I write this with a box, I'm going to write it as 2 sig figs. So I'll round 44 up to 45. So I want my 2 digits. So that'll be 45,000 amps, or 45 times 4.5 times 10 to the fourth. That would work. Or 45 kiloamps. That would work. Any number of these things, or all, as long as there are only 2 digits that are significant. That's fine. So there's my answer. And now you can, of course, see very, very obviously, right? Instead of 18 million watts of power that were lost, we're now only losing 45,000 watts of power. Still quite a bit of power to be dissipating, but much better than we were doing. Okay. So the next thing that I want to talk about is braking forces and eddy currents. So I think we can get rid of the PowerPoint because I have all of this written down. So I have this same example that we've looked at now several times, the magnetic force on a current carrying bar. So we said that if we moved this bar to the right, as long as the magnetic field took up all of the space, so I could keep drawing X's through all of this. As this bar gets bigger, my loop gets bigger, and that will induce a current that flows counterclockwise in this wire. And we've done this a couple of different ways now. But this way of thinking about it kind of makes it seem like we can get energy for free. Like, as long as this bar keeps moving, we can induce a voltage and a current. Well, I mean, geez, power is voltage and current. Right, and power is a lot like energy. So it kind of seems like if this moves, we just get free power. That's, of course, not what happens. That violates every law of physics that exists. Most importantly, the law of conservation of energy, which says that energy is never created or destroyed. So this energy needs to be coming from somewhere. Okay. And the answer to this is that to move this bar is not energy free. You have to pull on it. Okay. So in order to make this move, there has to be a pulling force. Okay. And if there's a pulling force that's pulling it to the right, well, that must mean that there's some sort of braking force that's pulling this to the left. And if these two are equal and opposite in magnitude, then we can have this bar traveling at a constant speed, because we know from Newton's first law that an object can travel at a constant speed. It doesn't speed up or slow down as long as there's no net force. Okay, so this is a little bit of a homework tip, which is there's a question that's like this. And this is sort of the hint for this, is that the question asks, how hard do you have to pull? What force do you have to use to pull? And the answer is that you need to figure out what the magnitude of this braking force is. And the only force that is really available to us is a magnetic force. So that would be something to think about. Okay. So braking forces like this always exist in induction. And I have a demo that I wanted to show you about this. Let me go grab it. Okay, so I have a magnet here, and this magnet doesn't stick to this aluminum piece of pipe, right? So aluminum is not a ferromagnetic material, so we don't have to worry about sort of there being any sort of sticking force from this going on it. Okay, if I put it on it, it doesn't do anything. But if I move a magnet in the presence of any conductor, even though this is not a ferromagnetic conductor, if I move it in the presence of this conductor, there will be currents that get induced in this pipe. And that's kind of crazy to think about, because this isn't a wire. We're used to thinking about currents as flowing through wires. But current is just the flow of charge. So when this magnet moves next to this piece of aluminum, there will be little currents that the magnet is here and it's moving here. There's little currents that are being induced in this pipe right along this time. And so a cool thing that happens here is what happens if I put this in the pipe. Let's see if I can find a view that you can see the whole pipe. So here's my whole pipe. It's kind of long, so we'll see how it works to get this in the view. So I put this in here, and I drop it. And it's still in the pipe. It still hasn't come out of the pipe. Still in the pipe. It finally came out. So what was going on is that as this magnet flowed through the pipe, there was little currents that were being induced in the pipe as it moved through. So there's now not just one force acting on this, right? I drop it, the force of gravity acts down. But there is always a force that opposes that force of motion. It'll be a magnetic force that make it take forever to get through. When currents like this are produced inside something that's not a wire, we tend to call them eddy currents. So that's a term that you might see in the book or in your homework. But the eddy current, anytime you have an eddy current, there's a braking force, and that braking force will always be pointed in the direction that opposes motion. So it's our way that we are ensuring that energy is conserved. So there's lots of applications of eddy currents and braking forces in the real world. So here is one of them. So transcranial magnetic stimulation is a way that we can do several things with our brain. But one of the cool things is that we can use this sort of thing to figure out what parts of the brain are responsible for what sort of actions, right? So the way this happens is that you have a loop of current going around like that outside of your head. So you kind of wear a helmet or something that had a loop of current. And of course, a loop of current, we'll call this external, creates an external magnetic field. And so there'd be a magnetic field that goes like that through the center. And we can focus this external magnetic field on a section of the brain that we're interested in. And that will induce currents inside your brain. And this basically just messes up your brain, not for long term, but for the moment. So there is a current being induced inside your brain. And it basically stops the neurons in the stimulated region from working properly, right? The way that your brain sends and receives signals is by sending and receiving electric pulses from one thing to another. So if you turn it off, or if you interfere with how that behavior works for a moment, you will not be able to do that. So if you're, say, you're focusing this on a certain area of the brain that controls the motion of your right hand, all of a sudden your right hand stops working in a way that you are used to seeing it work. And it can be pretty exciting to see this. It's pretty interesting to watch because like they'll show videos of people talking and they'll be trying to talk and they'll show them a picture of an apple. What's that? And they sit there and they can't form the word apple because they know what it is, but they can't say it. Okay. Other ways that we use induction, this is a seismograph. So if, say, you want to know where there is an earthquake in a remote area, like on the top of a volcano where you don't really have scientists that live long term, you can put a permanent magnet on the ground and a little coil that can be on a spring. And if the ground moves up and down, this spring will move up and down. And a coil moving in the vicinity of a magnetic field will have a current induced in it. So if the ground moves up and down, there's a current in the wire, and that can send a signal up to a satellite somewhere. And almost instantly, we know thousands of miles away that the ground is moving there. And we have a pretty good idea how much the ground is moving because we know what the magnitude of the current is that was induced in that wire. Your book talks about motors. That's how motors work. Generators work this way. Metal detectors, you ever wonder how they know if you have metal in you? Induction. If you have a piece of metal in you anywhere, when you walk through a magnetic field, you are now, there's current that will be produced as a piece of metal travels through a magnetic field. If you have an electric toothbrush, it works this way. If you have, some people have cell phones that charge via induction, so you don't have to plug them in. You just kind of set them on a charging device that uses induction. I recently just got an induction cooktop. So instead of using heat to cook, it uses induction to cook. So it's really cool. There is like a coil of wire under the inside the cooktop, and when there is a piece of metal, like a pot, on top of it, and you turn it on, well, current will start flowing. So you, of course, can't use, say, a ceramic pot on your induction cooktop because your induction cooktop isn't made out of metal, or your ceramic pot isn't made out of metal, so you can't have induced currents in a ceramic pot. But it'll induce a current in your pot. And from our example with the power transmission, you know that a current is something that is heat. So that's how your pot heats up. And it's the coolest thing. It's totally different than an electric cooktop, right? I can have a pot of boiling hot water, and a pot of boiling hot water is hot, but not so hot that I can't touch it instantly. 212 degrees. I wouldn't put my hand in it and like hold it there, but I could stick my hand in the water and pull it out and it would be fine. And I can do this on my cooktop. I boil water, I take the pot off, and I go like that with my hand. It doesn't burn me. It's hot, but it doesn't burn me, right? So there's a lot less heat that's lost in this. It's a pretty cool device. I'm obviously very excited about it. It's my new toy. This is how microphones work too. So sound waves is a future topic in this class. We'll get there in about a week. As the membrane, as a sound wave passes through a membrane, it will make this bounce back and forth because a wave is passing through it. And there's a little coil of wire inside that membrane. So as the coil of wire moves back and forth in the presence of a magnetic field, there will be a current that's induced in this wire. If you send that out to an amplifier, you can amplify your voice. So all sorts of things. Before I totally finish with induction, I just wanted to remind you some of the most important things before you go off on your way and do your homework. So we started off this chapter talking about magnetic fluxes, okay? So this is the thing that measures the amount of magnetic field that passes through a surface. So, and usually with surface, we're talking about loops of wire. So the magnetic flux that goes through a loop of wire depends on the area of that loop A, the strength of the magnetic field that is in the presence of that wire, and also this angle. And this was a sort of tricky angle where we were thinking about the angle here that is made between the magnetic field and this line here, which is coming out perpendicular from our loop of wire. Next thing that we used was Lenz's law, and this was the law that allowed us to determine the direction of an induced current. So it said that there'd be an induced current in the loop if the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposes the changing flux. So something that you should commit to memory or write down or whatever it is that you need to do is that the induced magnetic field will point in the same direction as the external magnetic field if the magnetic flux is increasing. The induced magnetic field will point in the opposite direction as the external magnetic field if the magnetic flux is decreasing. So let's write that down. So if flux is increasing, B induced is opposite of B external. If the flux is decreasing, so that's a magnet going farther away from the loop of wire or the battery turning off or something like that, B induced is same direction as B ext. So that's the thing that we use for Lenz's law. And then we used Faraday's law to learn the magnitude of the induced voltages and currents. So the magnitude of an induced voltage depends on the change in flux over the change in time. And if you have a coil of wire, then you'd multiply this by the number of loops in your wire. And then once you have a voltage, you can use Ohm's law to figure out the magnitude of an induced current. And the last thing to remind you about is we also started off this chapter talking about motional EMFs as being the motion of a conductor that goes through a magnetic field will produce this charge separation because it produces opposite forces on different charges. And this gives us another equation to use for figuring out what the induced EMF would be. So we actually have two different equations that will tell us the induced EMF. This one here and this one here. And you can actually, some of these problems you can use either one. A lot of the times you can use either one. But usually there's one that's better than the other. It makes your life a little bit easier. So we'll do both of those too. All right, that finishes off chapter 21. I'll be back with one more video to go over some problem-solving recitation style worksheets, and then we'll move on to the next chapter.